Alright, concept B is going to focus on defining and exploring Arrhenius acids and Arrhenius bases. Now, Arrhenius acid is defined as a substance that is going to release hydrogen ions as the only positive ion in aqueous solution. Now, just realize there are many substances that contain hydrogen that are not acids, especially when we see them covalently bonded to carbon, which we'll explore more in our organic chem unit, such as CH4 and methane. So just realize you have a table in your reference tables that you can go to get some examples of this, and we'll talk a little bit more about it in class so we can figure out and compare Arrhenius acids to other substances. Alright, a proton, we're going to see here, when we release this hydrogen into an ion, it's actually just left with one proton. So a hydrogen ion is sometimes referred to as a proton when we talk about acids and bases, and that's because it loses its electron. However, this cannot exist alone in water, so it is attracted to the unshared pairs of electrons on the water. And so this creates what we call the hydronium ion. So a lot of times we're going to interchangeably use the hydrogen ion and hydronium ion. They both are going to give a substance its acidic properties. This is specifically called protonation. It's an addition of an acid's hydrogen ion, proton, to a water molecule to form a hydronium ion. Alright, for example, we have HCl, or hydrochloric, that's going to dissolve in water, and its acidic properties are a result of the positive hydrogen ions produced. So as you can see here, we're going to have hydrochloric acid that's getting dissolved into water to produce the hydrogen ions and the chlorine ions. But it's the hydrogen ions that we're looking for that's going to give those acidic properties. Now, an Arrhenius base is a substance that releases hydroxide ions as the only negative ion in aqueous solutions. Now again, realize that not every compound that contains OHs are bases. We're going to see in our organic chem unit that a lot of times OHs are going to represent an alcohol that does not ionize. So a very common example that comes up on the region exam is methanol, CH3OH. This is not a base, it is not an acid, it is just a regular substance. Here we have NaOH, sodium hydroxide, that's dissolving in water, and its basic properties are due to that hydroxide ion that is produced. Now, neutralization reactions, and many of you guys know this from middle school science, that acids and bases can neutralize each other. They react to form a salt and water. When writing these neutralization reactions, you're completing double replacement reactions, which, honor students, you've done a lot of work with this, so you should be able to make some connections to some previous units here. With our general reaction, we have an acid plus a base that is making water, and also what we refer to as a salt. So for example, we have hydrofluoric acid reacting with sodium hydroxide. This is producing water, so the H and OH are going to produce my water. And then you have sodium fluoride, which is produced from the negative ion of our acid and our positive ion from our base. And this is referred to as the salt. So really the reaction looks more like this. Remember, when we write our total ionic equation for honor students, you should know what that is from a previous unit, where we're breaking apart all of our aqueous ions into their separate ions. Here I've just left out their aqueous next to them. So if this is really what it's like in solution, then we can get our net ionic equation, which is H plus our hydrogen ion plus our hydroxide ion making water. This shows that Na and fluorine ions are considered spectator ions. They're there, they're just not participating in the chemistry of the neutralization reaction. When acidic and basic solutions are mixed, the hydrogen ion of the acid and the hydroxide ion of the base are going to form water. A lot of times you'll see for this unit I'll write water as HOH, just so that we can see the double replacement reaction clearer. The anion of the acid and the cation of the base are going to come together to form that salt. So here we're going to show that our hydrogen ion and our hydroxide ion are going to form water. And then our leftover potassium and chloride ions are going to then form our salts. Make sure that you check their oxidation numbers, and also make sure that the positive ion is always written first. So here we have our positive potassium ion written, followed by the negative chloride ions. And this is +1, -1, so that's why they are 1 to 1. And then it will be aqueous, which you can always double check on table F. And then finally we have here sulfuric acid plus lithium hydroxide. These are going to react to form, again, water, keeping in mind that just because we have two hydrogens here, we're not going to carry that 2 over to our water. Water is always going to be H2O. And then we're going to combine our spectator ions to make our salt. And here I have to balance out their charges. Lithium is only +1. Sulfate is -2, so I need 2 lithiums. And then now that I have my water and salt written down, I can go ahead and balance the equation to take care of the 2 lithiums and 2 hydrogens and hydroxide ions. And that's it. All right, so make sure you have your notes filled out. You don't need to go and do any quizzes or summaries for this unit, so you can just go ahead and make sure you have your notes all set.